A message sent from Neptune would take 4 hours just to reach Earth. By the time an answer came back, an emergency could already be over. The sun there is 900 times dimmer than it is here. Earth is too faint to see with the naked eye, and any crew that made the journey would be farther from help than any humans in history. This is not science fiction. It is what distance does when a planet is almost 3 billion miles away. If calm, thoughtful space journeys like this help you relax, please like, subscribe, and share the video so Boring Space Sleepy can keep creating them. Thank you for spending your time here. In the comments, tell us where you're watching or listening from, and what time it is in your part of the world. Now, follow the sunlight outward until home becomes a signal crossing the dark. The familiar picture of the solar system often begins with a clean row of worlds, each planet set beside the next as if the whole arrangement could be understood at a glance. Mercury sits near the Sun, Venus follows, Earth appears with its small moon, then Mars, Jupiter, Saturn, Uranus, and Neptune. The sequence is correct, but the spacing is not. In that compressed picture, Neptune looks like the last address on a long but orderly street. It appears distant, yet still part of the same visual pattern. The eye moves from one planet to the next without feeling the true gaps between them. That simple diagram has taught generations to think of the solar system as a compact family of planets, when in reality it is mostly distance, mostly emptiness, and mostly beyond the scale that ordinary human intuition can hold. The problem is not that the diagram is careless. A true scale diagram would be almost impossible to place on a classroom wall, because the planets would become tiny marks separated by long stretches of blank space. The sun would dominate the inner system, while the worlds themselves would be reduced to small points. Neptune would not sit politely beyond Uranus. It would be far away, separated from the warm inner planets by a span so large that the familiar picture would lose nearly all of its visual comfort. The distance from Earth to the Sun is called 1 astronomical unit. It is about 93 million miles. Neptune orbits at an average distance of about 30 astronomical units from the Sun, which means its path lies roughly 30 times farther out than Earth's. Written as a number, the distance is about 2.8 billion miles. That figure is accurate, but it is not very useful to the human mind. Large numbers can be repeated without being felt. They become labels instead of experiences. To understand Neptune as a destination, the distance has to be brought down into a scale small enough for the body to recognize. A simple model can begin with the Sun represented by a basketball. At that scale, Earth is not another ball nearby. It is a tiny bead, only a few millimeters wide, placed about 86 feet away. Mars sits farther out, still within a distance that feels manageable. Jupiter, much larger than Earth, would be a small marble several hundred feet from the basketball. Saturn would be farther still, but still close enough that a person walking across an open field could reach it without the journey feeling impossible. This is the region of the solar system that often fills the imagination: the rocky worlds near the Sun, the asteroid belt, the giant planet Jupiter, and the ringed planet Saturn. Even here the distances are large, but they remain within a scale that can be crossed in a short walk. Uranus changes the feeling of the model. It is no longer simply a little farther down the same line. It sits several blocks away from the basketball, far enough that the Sun no longer feels like a nearby object in the scene. Neptune lies farther again, about half a mile from the basketball in this model, represented by a small bead held at a distance where the original Sun model may no longer be visible at all. The result is plain and important. The inner planets are clustered close to the star. Jupiter and Saturn are far by human standards, but still belong to the more crowded inner architecture of the system. Uranus and Neptune occupy a much lonelier region, where the gaps themselves become the main feature. This is what the classroom row hides. The solar system is not a chain of evenly spaced worlds. It is a bright centre with a tight inner group, then a broad outward thinning, then planets moving through a remote zone where the sun's presence is still gravitationally dominant, but visually and energetically reduced. Neptune is not just another step beyond Saturn. It is part of the distant outer architecture, where the meaning of travel changes. A spacecraft travelling outward does not move through a busy landscape of nearby planets. It crosses enormous intervals in which there is almost nothing to see and almost nothing to mark progress. For months and years, the sun slowly contracts behind it, while the destination ahead remains a faint point. Most of the journey is not arrival, discovery, or encounter. Most of the journey is empty transit. Human beings are not naturally prepared to understand that kind of distance, because everyday life offers no comparison. A journey across a city can be felt. A journey across a continent can be planned around roads, aircraft, time zones, and fuel. Even the distance to the moon, though immense by ordinary standards, remains close enough for radio conversation with only a brief delay. Neptune belongs to a different scale. The separation is so large that even light, the fastest known thing in the universe, takes more than 4 hours to travel from the Sun to Neptune. Sunlight reaches Earth in a little over 8 minutes. At Neptune, that same light has been travelling for more than half of a working day. This is not only a fact about brightness, it is a fact about information, communication, and the basic structure of any mission that tries to go there. Because radio signals also travel at the speed of light, every message between Earth and Neptune must cross that same span. A question sent from Earth cannot be answered quickly, not because of weak equipment, but because the universe has a speed limit. The delay is built into the distance itself, before any discussion of fuel, life support, radiation, or psychology. Neptune imposes this first condition. Earth is no longer near enough to behave like an immediate partner. That condition begins with scale. The same scale also changes how speed is understood. The fastest crewed spacecraft humans have flown would appear almost motionless in a model of the solar system large enough to show Neptune's real separation. Speeds that seem extreme near Earth become small against the geometry of the outer planets. A vehicle travelling tens of thousands of miles per hour can still require many years to cross the gap. The difficulty is not simply that Neptune is far away, it is that the distance is large enough to turn speed into something less reassuring. There is no direct road, no steady engine burn that simply carries a crew outward like an aircraft crossing an ocean. Interplanetary travel depends on orbits, launch windows, gravity assists, propulsion limits, and the need to slow down at the destination. A robotic spacecraft can fly past Neptune at high speed and keep going. A crewed spacecraft cannot treat the planet as a brief target. It must arrive with enough control to survive, observe, maneuver, and possibly enter orbit. That requirement makes the distance even more severe, because reaching Neptune is not the same as passing Neptune. The mission must spend energy not only to depart the inner solar system, but also to manage the arrival at the far end. This is where the neat row of planets becomes actively misleading. It suggests a journey made of locations, as if the problem were simply moving from one planetary dot to another. In practice, the spaces between the dots are the mission. They determine the years of confinement, the delay in communication, the amount of shielding, the reliability demanded from machines, and the psychological burden placed on the crew. The planets themselves are brief islands in a system whose dominant reality is separation. Neptune, as the outermost major planet, makes this separation unavoidable. It is still inside the solar system. It still orbits the same star. It still belongs to the same gravitational family as Earth. Yet it stands far enough away that human ideas of nearness begin to fail. The Sun is still the Sun there, but it is no longer the Sun as life on Earth knows it. Earth is still present in the same system, but it is no longer visually available to the unaided human eye. Mission Control is still listening, but it is no longer present in the living moment of decision. All of these later consequences begin with the same quiet fact. The distance has been hidden from view by the diagrams used to make the solar system understandable. Those diagrams are useful for names and order, but not for reality. They teach sequence, not scale. They make Neptune appear reachable in the same mental category as the other planets, when the actual journey would carry a crew beyond any environment human beings have ever occupied. The first step toward understanding Neptune is therefore not the planet itself, but the empty distance before it. That distance changes the Sun, changes communication, changes risk, and changes the meaning of home long before the spacecraft ever arrives. Neptune was first approached by calculation before it was ever confirmed by sight. That fact gives the planet a different place in the history of astronomy, because its discovery did not begin with a bright object moving clearly across the sky. Mercury, Venus, Mars, Jupiter, and Saturn were known in antiquity because they could be seen without instruments, wandering against the fixed background of stars. Uranus entered the record much later, after telescopes made the sky deeper and more detailed. But even Uranus was found through observation first. William Herschel noticed it in the late 18th century while surveying the heavens, and only afterward did astronomers recognize that the object was not a comet, but another planet. Neptune followed another path. It emerged because Uranus did not quite behave as expected. Its orbit could be predicted using Newton's law of gravity, and for much of the path the predictions worked. Yet over time the planet appeared slightly displaced from where the calculations placed it. The mismatch was small, but it persisted. It did not look like a spectacular failure of physics. It looked like a pressure on the edge of precision, a difference between theory and measurement that could be ignored only for a while. Astronomers had several possible explanations. The observations might have errors. The orbit of Uranus might have been calculated from incomplete data. The law of gravity itself might require adjustment at great distances from the Sun. Another possibility was more direct. A planet beyond Uranus could be pulling on it, too faint to have been recognized, but massive enough to disturb its motion. This was the idea that made Neptune possible before Neptune had been seen. The important feature of this moment is its restraint. No one was looking at a visible blue disk and trying to name it. The evidence was indirect. A known planet was moving under the combined influence of the Sun, the other planets, and perhaps an unknown body still farther out. To extract that hidden body from the motion of Uranus required patient mathematics. The task was not simply to say that something might be there. It was to estimate where it had to be, how far from the Sun it might orbit, and how strong its pull would need to be in order to produce the observed disturbance. Urbain Le Verrier in France worked through this problem with unusual determination. John Couch Adams in England also carried out related calculations. Their work belongs to a period when astronomy was becoming increasingly mathematical, not replacing the telescope, but extending what the telescope could be asked to find. Le Verrier sent his predicted position to Johann Gottfried Galle at the Berlin Observatory. In September of the mid-19th century, Galle and Heinrich d'Arrest searched near that calculated location and found the planet very close to where the numbers had placed it. A world that no human eye had recognized before was brought into view because another planet had leaned slightly away from its expected path. This discovery matters for more than historical pride. It shows that Neptune has always been known first as a gravitational fact, before it became an image, before its atmosphere Winds, moons, and colour could be studied. It was a solution to a problem in motion. The planet announced itself by changing the behaviour of something else. That is a quiet but powerful way for a world to enter human knowledge. It also says something about the limits of human senses in the outer solar system. Neptune is too faint to stand out naturally in the night sky. It does not offer itself to ordinary vision. The sunlight it reflects is weak by the time it returns across such a wide distance, and its apparent size is small. Through a telescope it becomes a disk, but without one it is effectively absent from normal human experience. For most of history, people lived under a sky that contained Neptune without knowing it was there. The planet did not become real to science because the sky made it obvious. It became real because a pattern failed to close until an unseen cause was added. That remains one of the central lessons of Neptune. Much of what is important in the outer solar system cannot be approached through direct familiarity. It has to be inferred from motion, light, timing, temperature, and the behaviour of instruments designed to extend perception far beyond the body. The same principle continues in modern planetary science. A spacecraft does not feel Neptune's atmosphere in any ordinary way before arrival. It measures fields, spectra, particles, and changes in trajectory. A telescope does not experience Neptune as a nearby world. It gathers faint light, separates wavelengths, and reconstructs properties from signals that have crossed billions of miles. Even the planet's deep interior remains mostly inferred, because no probe has descended into those pressures and returned a direct report. Models must combine mass, radius, heat flow, atmospheric chemistry, and magnetic field measurements to estimate what lies below the clouds. Neptune is therefore not only distant in space, it is distant in method. It asks science to work through traces rather than through simple contact. The original discovery through Uranus was the first example of that relationship. The unseen planet affected the seen planet, and the effect became evidence. This does not make the discovery less physical. It makes it more revealing. Gravity is not an idea imposed on the sky. It is a measurable interaction. Uranus moved differently because mass existed beyond it. The mathematics did not invent Neptune. It narrowed the search to the region where a real body could be found. When the telescope confirmed the prediction, the results strengthened confidence in a scientific method that can use small deviations to locate large causes. At the same time, the discovery was not perfectly simple. Later analysis showed that the predicted orbit and the planet's actual orbit were not identical in every respect, and the historical credit involved more than one calculation and more than one observer. The essential point remains clear without turning the story into a legend. Neptune was confirmed through a partnership between theory and observation, and the partnership worked well enough to reveal a new planet. For a future crew, that history would not be a distant anecdote. It would describe the same kind of environment they were entering. Neptune would not become easy to know merely because human beings had arrived nearby. The planet's strongest realities would still resist direct access. Its winds could be observed and measured, but not safely entered by any crude vehicle. Its deeper layers would remain unreachable under crushing pressure and heat. Its magnetic field could be mapped, but its source inside the planet would still require interpretation. Triton's geysers could be sampled more directly than ever before, yet the deeper question of a possible subsurface ocean would still depend on gravity measurements, surface geology, chemistry, and thermal models. Arrival would improve the evidence, but it would not remove the need for inference. That is part of what makes Neptune scientifically serious. It does not reward the idea that exploration is simply a matter of going somewhere and seeing everything plainly. It shows that even proximity has limits. A crew could cross billions of miles, enter orbit around the distant planet, and still face a world whose most important processes remain hidden below clouds, ice, and compressed layers of material. The journey would bring human instruments closer, but not make the planet transparent. In this way, Neptune's discovery prepares the mind for the mission's deeper challenge. The planet was found because science learned to trust a disciplined absence. Uranus was not where it should have been, and that difference pointed outward. A future mission would live with similar absences on a larger scale. The crew would not see Earth with the unaided eye. They would not hear mission control in the present moment. They would not feel the sun as warmth. They would work through delayed messages, remote signals, instrument readouts, and careful reconstruction. Neptune's first appearance in human knowledge was not a picture, but a consequence. That remains the proper beginning for understanding it. The planet stands at the far reach of the familiar solar system as a reminder that reality does not need to be visible to be active. Long before human beings could imagine travelling there, Neptune was already shaping the path of another world, quietly proving its presence through a pull that mathematics could follow across the dark. At Neptune, noon would not feel like noon. The sun is still the central star of the system, still the object holding the planets in their orbits. But by the time its light reaches Neptune, it has spread across a far larger sphere of space. The same energy that feels bright and direct on Earth arrives there reduced to a small fraction of its familiar strength. Sunlight weakens with the square of distance. So a planet about 30 times farther from the sun than Earth receives about 900 times less solar energy. This is not a small dimming. It is a transformation of the environment. The surface of Earth has clear days, shadows, colour, heat, glare, and an ordinary sense that daylight is the active condition of the world. Neptune receives something closer to a persistent deep twilight. The sun would still be visible as a sharp point, brighter than any other object in the sky, but it would not fill the surroundings with the kind of light that shaped human eyes, human sleep, human chemistry, and the daily rhythm of life. The difference matters because daylight on Earth is not only illumination, it is a biological signal. Human bodies use light to organize internal time. Bright morning light helps regulate the circadian rhythm, the internal cycle that influences sleep, alertness, hormone release, digestion, temperature, and mood. The effect is not vague. Specialized cells in the eye respond to blue-rich light and send timing information to the brain. That information helps keep the body aligned with the outside world. On Earth, sunrise and sunset are not merely scenery. They are part of the machinery by which the body knows when to wake, when to rest, and how to pace its internal processes. A crew travelling toward Neptune would gradually lose the natural version of that signal. Long before arrival, the sun would be smaller, weaker, and less useful as an environmental clock inside the spacecraft. Artificial lighting would have to replace what the solar system no longer provides. It would need to deliver brightness, timing, and colour changes carefully enough to support sleep and alertness through years of confinement. This is already important in low Earth orbit, where astronauts experience rapid cycles of sunlight and darkness as the spacecraft circles Earth. It would become far more important on a Neptune mission, because natural daylight would no longer be a reliable partner. The crew would live in a constructed day. Morning would be created by lamps. Evening would be created by dimming schedules. The sense of a normal day would depend on engineering, discipline, and the health of lighting systems that cannot be allowed to fail. That dependence sounds ordinary at first, because people on Earth already live under artificial light. Offices, hospitals, ships, submarines, and polar stations all use lighting to manage work and rest. The difference is that all of those environments remain tied to a larger planet where outdoor daylight still exists nearby or returns with the season. At Neptune, there is no surrounding world of ordinary daylight. The dim sun outside the window cannot restore the body by its own force. It cannot warm skin through a suit. It cannot fill a room through glass and make the brain believe that morning has truly arrived. The spacecraft must provide nearly everything that Earth once provided without effort. Light becomes life support, not decoration. The psychological effect of that change would build slowly. At first, the crew might treat the shrinking sun as a sign of progress, a visible measure of the distance already crossed. Later, as the mission stretches across years, the loss of sunlight would become less symbolic and more practical. The human nervous system does not respond only to knowledge, it responds to conditions. A person can know that a lamp is scheduled to imitate dawn, while the deeper body still registers that the real star outside has faded to a distant point. That does not mean the crew would inevitably collapse under the absence of strong sunlight. Careful lighting, exercise, nutrition, medication when needed, and psychological support could reduce many effects. But the mission would be asking biology to accept a substitute for one of the oldest environmental patterns in human evolution. For every generation before spaceflight, the sun rose as a real presence in the sky. Even in winter, even through cloud, even at high latitudes where daylight could become brief, the cycle belonged to Earth. A Neptune crew would move beyond that direct inheritance. They would carry the pattern with them because they could no longer receive it naturally. The faintness of the sun also changes energy. Near Earth, sunlight is abundant enough that solar panels can power spacecraft efficiently. Farther out, solar power becomes less practical. At Neptune, the weakness of sunlight means a crewed spacecraft could not rely on ordinary solar arrays in the same way missions near Earth or Mars might. Robotic spacecraft travelling to the outer planets have often used nuclear power sources, because sunlight becomes too faint for compact solar systems to provide enough reliable energy. A human mission would require far more power than a small probe. It would need to run life support, heating, communication, navigation, laboratories, computing systems, medical equipment, exercise devices, lighting, food production experiments, and possibly propulsion or orbital operations. The farther the spacecraft travels, the more energy becomes not only a technical requirement, but a form of environmental protection. Without power, the crew loses heat, air circulation, water recycling, lighting, and the controlled conditions that keep the habitat alive. The dim sun outside would not be able to help quickly. It would not pour energy onto the vehicle in a useful abundance. The spacecraft would have to bring its own dependable source of warmth and electricity across billions of miles. This makes Neptune feel less like a destination under a weaker sky, and more like an environment that must be carried against the natural direction of the solar system. Earth gives energy freely in the form of sunlight, weather, open air, and a biosphere that renews itself on huge scales. A spacecraft to Neptune must manufacture a small, enclosed version of livable conditions from stored machinery and fuel. The crew would be surrounded by a universe that contains energy in enormous amounts, but almost none of it would be available in the form human life can use. The star that powers Earth would still be there, but its practical generosity would be mostly gone. The light conditions at Neptune would also affect the way the planet itself appears. Neptune is often shown as a vivid blue world in images, and its colour is real, connected to methane in the atmosphere absorbing red light and leaving more blue light to scatter and reflect. But a human observer nearby would not see the planet under Earth-like illumination. The available sunlight would be weak, and the visual scene would depend heavily on instruments, long exposures, and enhanced imaging. the planet would still be beautiful, but not in the bright, immediate way that photographs can suggest. Its cloud bands, storms, and colour contrasts would be measured with cameras and sensors designed to collect faint light carefully. Human eyes at a window would see less. This distinction matters because exploration is often imagined as direct seeing. At Neptune, direct seeing would be limited not only by distance from Earth, but by the reduced light that reaches the entire region. The spacecraft would have to turn faint signals into usable knowledge. It would gather photons patiently, separate wavelengths, and translate low-light data into images and measurements that the human eye alone could never assemble. The same would be true for any view of Triton, the rings, the small inner moons, and the space around the planet. The crew would be present, but their presence would be mediated by instruments almost constantly. The outer solar system does not become bright and clear simply because human beings have arrived. It remains faint, cold, and dependent on careful measurement. This is the central change introduced by Neptune's sunlight. The planet is not only far away in miles, it is far away in the basic environmental language that life on Earth understands. The day is dim. The sun gives little warmth. Power must be carried or generated internally. Vision depends on instruments. The body's clock depends on artificial timing. The familiar bond between sunlight and living rhythm is weakened until it has to be rebuilt inside metal walls. That rebuilding could succeed technically, but it would never be the same as standing under Earth's sky. A crew at Neptune would not live in darkness, and the mission should not be imagined as a descent into blackness. The more accurate condition is quieter and more difficult a place where the sun remains visible but no longer behaves like home, where daylight exists as a pale reminder of its former strength, and where the ordinary meaning of noon has been left far behind. Earth disappears from ordinary sight long before a crew can fully understand what that disappearance means. From low Earth orbit, the planet is not an idea or point on a chart. It fills the window. Oceans, deserts, clouds, coastlines, storms, city lights, and the thin blue edge of the atmosphere remain close enough to be seen as parts of a living world. Even the moon, distant by the standards of human history, still offers astronauts a direct view of Earth as a bright disk in black space. That view gives distance a visible limit. The crew may be away from home, but home remains present to the eye. A mission to Neptune would remove that anchor. As the spacecraft moves outward, Earth first becomes a smaller disk, then a bright star-like point near the sun, then a target that must be located by instrument and calculation rather than by unaided sight. At Neptune's distance, Earth reflects too little light to stand out naturally to human vision. It still exists in the same solar system, still moves around the same star, and still contains every person, ocean, forest, city, and memory the crew has left behind. But at the window, without a telescope and careful pointing, it is gone. This is not a poetic absence. It is a consequence of light, distance, and the limits of the human eye. A planet is visible because it reflects sunlight, and that reflected light weakens as it spreads outward across space. Earth is bright when seen from nearby because it has clouds, oceans, ice, and an atmosphere that scatter sunlight well. From the moon, that brightness is unmistakable. From Mars, Earth can still appear as a noticeable point under favourable conditions. From the region of Neptune, the problem changes. The sun itself is faint compared with its appearance from Earth, and the light reflected by Earth must travel across the wide inner solar system before reaching the observer. The signal becomes too small for ordinary vision to treat as a meaningful object. The crew could find Earth with optical instruments. A telescope could be aimed towards the correct coordinates, and cameras could gather enough light to identify the planet. perhaps with the moon nearby as a companion point. But such a view would be planned, magnified, processed, and confirmed. It would not be the same as looking out and seeing home directly. That distinction matters because human beings do not live by knowledge alone. A person can know that Earth is there and still feel the loss of seeing it. Space agencies have long recognized the psychological value of viewing Earth from orbit. Astronauts often spend personal time photographing the planet, tracking familiar regions, and watching weather systems unfold far below. The activity is scientifically useful, but it is also emotionally important. Earth observation offers color, movement, scale, and reassurance inside an artificial environment. It reminds the crew that the spacecraft is not the whole world. It shows that the ordinary planet continues beneath them, close enough to be visually present even when physically unreachable. On the International Space Station, this view is part of daily life. The station crosses sunrise and sunset many times in a single Earth day, and the planet below changes constantly. A crew member may look down at the Sahara, the Pacific, the Himalaya, or the lights of a city at night. The window becomes a point of orientation, not only in space but in identity. The crew is off the planet, yet still circling it. The mission is extreme, but it remains tied to a visible home. A Neptune mission would replace that condition with a far more distant one. For years, the spacecraft would travel with no large world below, no blue horizon, no visible continents, and no natural scene that carries human meaning. The windows would show the sun shrinking, stars holding nearly steady, and occasional planetary targets only when the trajectory allowed. Most of the time, there would be no landscape outside at all, only the controlled interior and the measured emptiness through which the vehicle moved. This absence would not be dramatic every moment, it would become ordinary, and that ordinariness is part of the difficulty. The crew would adapt to living without a visible Earth, using schedules, images, messages, recordings, private routines, and shared work to preserve connection. Digital archives could contain views of Earth, family videos, recorded sounds, maps, music, and personal memories. These tools would help, yet they would all share one limitation. They would be representations of Earth, not Earth itself. The live planet would no longer be part of the immediate visual field. The crew would be surrounded by reminders of home while knowing that the actual world has fallen below natural sight. During an ordinary mission close to Earth, that difference can be narrowed by the window. At Neptune distance, it cannot. The loss also changes the meaning of direction. Near Earth, outward and homeward are easy to understand. Earth is below, the moon is ahead, the planet is a visible reference. Farther out, navigation becomes a matter of coordinates and instruments rather than bodily orientation. Earth lies inward toward the sun, but the sun itself has become a small and intense point. The home planet is hidden in that same general direction, too faint and too close to the glare of the star from many viewing angles to serve as a simple landmark. The crew can calculate its position precisely, but calculation does not provide the same comfort as sight. This is one of the quiet shifts of deep space travel. The human sense of place becomes less sensory and more abstract. The ship knows where it is through tracking signals, star positions, onboard clocks, and orbital models. The crew knows because the instruments say so. The body receives less direct confirmation. There is no ground below, no horizon, no weather, no changing daylight that belongs to a planet. The spacecraft becomes the only immediate environment. Everything else is data. For a short mission, that may be manageable as a temporary condition. For a journey measured in many years, it becomes a long-term setting for thought and emotion. The absence of Earth from view would also separate a Neptune crew from one of the most powerful experiences reported by astronauts the recognition of Earth as a whole. From orbit or lunar distance, Earth can appear as a single fragile system, without visible borders and with a thin atmosphere surrounding all known life. This view has often been described as changing how astronauts think about the planet. At Neptune, that whole Earth image would no longer be available directly. The crew would carry the memory of it, perhaps from training, perhaps from earlier parts of the mission, perhaps from images made by previous spacecraft. But they would not be able to refresh it with ordinary sight. The farther they travelled, the more Earth would belong to memory and records. Messages from home would continue, but they would arrive after long delays. News would arrive as packets of information. Family life would continue without shared moments. Birthdays, illnesses, changes in cities, discoveries. Ordinary days of weather and work on Earth would reach the spacecraft as delayed fragments. The visual loss and the communication delay would reinforce each other. Earth would be both unseen and out of sync. It would remain real, but less present. A crew member might look at an image of Earth taken by an onboard telescope and understand its coordinates, its phase, its distance, and its brightness. The image might show a small pale point, perhaps with a second smaller point beside it. Scientifically, that would be enough to confirm the planet's location. Emotionally, it would be a compressed version of everything human life has ever known. The scale would be difficult to reconcile. The same point would contain childhood homes, launch sites, oceans, languages, fields, hospitals, schools, and every person capable of receiving the crew's transmissions. The mind can understand this, but understanding does not enlarge the point. It remains faint. It remains remote. It remains something that must be found deliberately. This is why reaching Neptune is not only a test of propulsion and life support, it is also a test of whether human beings can remain psychologically whole when the planet that formed them is no longer a visible companion. The challenge is not constant fear. It is a quieter pressure, the steady removal of ordinary confirmation that home is near, shared, and accessible. The crew would still belong to Earth biologically, culturally, and personally. Their bodies would carry its gravity in their bones, its atmosphere in their lungs, and its sunlight in their circadian memory. Their language, tools, training, and mission purpose would all come from Earth. Yet the sky outside would not return that belonging in any direct way. It would show a distant sun, a field of stars, and eventually Neptune itself. Earth would be known, tracked, remembered, and loved, but not simply seen. By the time the spacecraft reached Neptune, the loss would already have become part of the mission's inner life, shaping how every view outward was understood. The first sight of Neptune would be remarkable, but it would arrive after the disappearance of another world from ordinary vision. The crew would not only be approaching a distant planet, they would be arriving in a region where home had become too far away for the eye, and where connection had to survive without the oldest proof of presence, the ability to look back and see where life began. The communication problem at Neptune begins with a simple physical limit. A radio signal does not cross space instantly. It travels at the speed of light, and at Neptune's distance that speed is no longer fast enough to preserve conversation. A message sent from Earth takes roughly 4 hours to reach a spacecraft near Neptune, depending on the exact positions of the planets in their orbits. A reply takes roughly 4 hours to return. One question and one answer occupy about 8 hours before any further clarification can begin. This delay is not caused by weak antennas or poor planning. It is the time required for information itself to cross the space between the inner solar system and the far outer planet. Near Earth, human spaceflight depends on a very different condition. Astronauts in low Earth orbit can speak with mission control almost in real time. The delay is so small that it feels like an ordinary conversation. When a sensor behaves strangely, when a procedure is unclear, or when a crew member needs medical advice, the ground can respond immediately. Specialists can examine live data, compare it with stored models, and guide the crew step by step. The spacecraft may be dangerous, but it is supported by a large human system on the ground. Engineers, doctors, flight directors, psychologists, and mission planners are not physically present, yet communication makes them part of the active environment. Their knowledge enters the spacecraft while the problem is still unfolding. At Neptune, that environment disappears. Mission control still exists. The experts are still listening. The network of antennas on Earth can still receive and transmit. But the support has been moved out of the present. If the crew reports a problem in the morning, the first response cannot arrive until many hours later. By then, the situation may have changed, worsened, or already been solved by the people on board. The message from Earth may still be valuable, but it no longer functions as immediate help. It becomes guidance from a previous version of the emergency. This is the central difference between delay and distance as daily experience. A short delay irritates communication. A long delay changes its nature. It turns a conversation into correspondence. At a few seconds, people can still interrupt, clarify, and adjust to each other. At several minutes, real-time cooperation becomes strained. At several hours, it no longer exists. The crew must describe a situation, act without waiting, and later compare their choices with advice that arrives after the fact. The ground cannot share the moment of decision. It can only receive its report. This would affect every part of the mission, but emergencies show the problem most clearly. A pressure seal begins to leak. The rate is not catastrophic, but it is increasing. The crew checks the sensors, isolates compartments, inspects the structure, and searches the maintenance database. They send Earth a detailed report with pressure readings, images, sound recordings, and the steps already taken. Then they continue working because there is no practical option to pause. 4 hours later, Mission Control receives the report. Engineers begin analysing it, but their understanding already belongs to the past. They do not know whether the leak has stabilised, whether a repair has been attempted, or whether the crew has discovered a second failure. They prepare recommendations and send them back. 4 hours after that, the instructions arrive at the spacecraft. 8 hours have passed since the first report. In that interval, the leak has become either controlled, critical, or irrelevant because the crew has already made the decisive repair. The advice may improve the next step, but it cannot rescue the first one. The same delay would shape medical care. On a short mission near Earth, a flight surgeon can speak with an astronaut, watch symptoms develop, ask follow-up questions, and recommend treatment as new information appears. At Neptune, even a careful medical consultation becomes slow and partial. A crew member with severe abdominal pain can describe the location, duration, vital signs, and possible causes. Earth can respond with diagnostic suggestions many hours later, but pain changes, blood pressure changes, consciousness changes. A condition that is manageable at one point may become dangerous before the next answer arrives. The crew would need deeper medical training than any current astronaut crew normally requires, and they would need equipment and procedures designed for independence. They could still consult Earth, but in urgent moments they would function as the only medical team within reach. Psychological support would also change. Human beings in space do not rely only on equipment, they rely on contact, a familiar voice, a private conversation, and a timely response can help maintain stability during confinement and stress. Near Earth, a crew member can speak with family or a support specialist in something close to a shared present. The other person reacts to tone, pause, worry, fatigue, or humour as it occurs. At Neptune, that shared present is broken. A personal message becomes a recording sent across a 4-hour gap. The reply returns to a state that has already passed. The person who receives it may still value the care behind it, but the emotional timing has changed. Comfort arrives late. A misunderstanding takes half a day to repair. A family conversation no longer has the rhythm of conversation. It has the rhythm of letters, carried by light instead of ships, but still separated by time. This matters because isolation is not only the absence of people, it is the absence of responsive people. A crew at Neptune would not be cut off from Earth completely, and that distinction is important. They could receive news, instructions, entertainment, science updates, personal messages, and recorded conversations. They could send their own reports, images, observations, and private thoughts back home. The connection would continue, yet it would not surround them in the way near-Earth communication surrounds astronauts today. It would arrive in blocks, delayed and incomplete. It would inform, but it would not accompany. Over years, that difference could reshape the crew's relationship with the planet they came from. Mission control would become less like a room listening in real time, and more like a distant institution, exchanging carefully prepared packets of knowledge. Earth would still speak, but not at the pace of the life on board. Operationally, the mission would have to be designed around autonomy from the beginning. The crew could not be trained merely to carry out instructions. They would need authority to diagnose, prioritize, improvise, and accept risk without waiting for permission. The spacecraft would need intelligent systems capable of monitoring its own condition, identifying failures, and presenting options clearly. Manuals would need to be complete enough to stand in for unavailable experts. Spare parts, manufacturing tools, medical supplies, and software would have to be organized around the assumption that the crew is alone when the important decision comes. This does not mean artificial intelligence or automation would replace human judgment. It means the boundary between crew and mission control would move inward. More of the ground's role would have to be carried inside the spacecraft before launch. That requirement adds mass, complexity, and responsibility. A larger onboard knowledge base needs power, storage, maintenance, and protection from errors. Automated systems can fail or misinterpret unusual conditions. A crew given more independence must also carry the psychological load of knowing that their judgment is final in many situations. Earth can review the decision later. It can praise it, question it, or suggest alternatives. But later is not the moment when the valve must be closed, the medicine given, the circuit isolated, or the trajectory correction committed. The delay makes responsibility local. At Neptune, command is not only a hierarchy, it is a consequence of physics. Science operations would also feel the delay. A robotic probe near another planet already works with communication limits, using pre-planned commands and onboard systems to gather data. A human mission would add flexibility, but not immediate shared control. If a rare event appears in Neptune's clouds, if a plume rises from Triton, or if an instrument detects an unexpected particle environment, the crew cannot ask Earth what to do and receive a timely answer. They must decide which observations matter, how to adjust the plan, and what risks are acceptable while the event is still available. Earth scientists may have better collective expertise, but their advice will follow the event rather than join it. The crew becomes the first interpreter of the distant environment, not because they know more, but because they are there when the data appears. The 8-hour lifeline therefore remains a lifeline, but it is not the same kind of lifeline that has supported previous crews. It carries knowledge, memory, authority, and care across the solar system. It can help the mission learn, adapt, and endure. But it cannot restore immediacy. It cannot make Earth present at the moment of danger. It cannot let a doctor respond to the next breath, an engineer hear the next sound, or a family member answer the next sentence. At Neptune, the crew is still connected to humanity, yet separated from the shared timing that makes connection feel alive. The signal continues to travel, steady and precise. But every word arrives after the world that produced it has already moved on. The time required to reach Neptune changes the mission before the spacecraft ever sees the planet as more than a point. A fast robotic flyby can treat distance as a long coast, followed by a brief encounter, but a crewed mission cannot. Human beings must remain alive, healthy enough to work, and psychologically steady through the entire journey. They must arrive with judgment, strength, and usable equipment after years in an enclosed vehicle. Under propulsion systems close to those that can be seriously discussed today, a voyage to Neptune would likely take on the order of 12 to 20 years in one direction, depending on trajectory, launch opportunity, gravity assists, propulsion choices, and the need to slow down at the destination. The exact number could change with future technology, but the main fact would remain. The journey is not measured in months. It is measured in large portions of adult life. That makes it unlike any crewed mission attempted so far. A journey to the moon lasts days. A long stay in low Earth orbit may last months, sometimes more than a year for special missions. A serious Mars expedition is often imagined as lasting roughly 2 to 3 years, including the outbound flight, time near or on Mars, and the return. Even that duration is considered a major challenge for medicine, psychology, radiation protection, and life support. Neptune extends the scale so far that the comparison begins to lose its usefulness. A Mars mission asks whether a small crew can remain functional for a few years away from Earth. A Neptune mission asks whether a crew can live through a whole era of life inside a spacecraft, while the destination remains ahead and Earth recedes into delay and dimness behind them. The body is the first system that reveals the cost of that duration. In microgravity, muscles no longer work against body weight in the normal way. Bones no longer receive the same mechanical loading that helps preserve their density. Fluids shift toward the upper body. Balance systems adapt to weightlessness. The heart and blood vessels adjust to an environment where standing, walking, and lifting no longer mean what they mean on Earth. Exercise can reduce these effects, and modern space stations use carefully planned routines to protect muscle and bone as much as possible. But exercise is not a full replacement for gravity. It is a countermeasure, a daily effort to slow a process the environment keeps encouraging. On a journey that lasts many years, the question is not simply whether the crew exercises. The question is whether the countermeasures remain effective across time spans much longer than those experienced by astronauts today. A person who begins the journey in early adulthood may arrive at Neptune in middle age. The body that reaches the planet is not the same body that launched. It has been shaped by enclosed air, recycled water, artificial light, restricted movement, radiation exposure, and the absence of natural gravity. Artificial gravity is often proposed as a solution, usually by rotating part or all of the spacecraft, so that centrifugal acceleration presses the body outward and creates a substitute for weight. In practice, this would add major engineering demands. A rotating habitat must be large, stable, and connected safely with propulsion, antennas, docking systems, and laboratories. It must work for years without vibration, structural fatigue, or repair problems that become difficult far from Earth. A device that works for a demonstration is not the same as a system trusted with lives for decades. radiation adds another long-term pressure. Beyond Earth's protective magnetic field, the crew is exposed to galactic cosmic rays, which are high-energy particles arriving from outside the solar system, and to solar particle events, which can send bursts of radiation outward from the Sun. Shielding can reduce exposure, especially from solar events. But cosmic rays are difficult because they can pass through many materials. Heavy shielding adds mass, and mass makes propulsion harder. The longer the mission lasts, the more exposure accumulates. A few days beyond Earth is one risk, several months is another, many years is another again. The danger is not only immediate radiation sickness, though strong solar events can pose acute threats. It is also the slow accumulation of damage to cells, DNA, the nervous system, and long-term cancer risk. A Neptune mission would need storm shelters, careful monitoring, shielding strategies, and probably mission rules that accept risks far beyond those allowed for current crews. That acceptance would not make the risk disappear. It would only acknowledge that reaching such a distance requires entering a different medical category. The spacecraft itself ages along with the crew. Every pump, valve, fan, seal, bearing, cable, filter, computer, sensor, and joint has a lifetime. Some parts can be made redundant, some can be repaired, some can be replaced from spares, but over a mission lasting 12 to 20 years, redundancy is slowly spent. A spare part used in year 4 is no longer available in year 12. A repaired system may function, but perhaps with reduced margin. A component designed for a certain operating life may continue beyond it, yet with rising uncertainty. Engineers can test equipment on Earth, but testing cannot perfectly reproduce the combined conditions of radiation, vibration, thermal cycling, microgravity, and continuous use across a deep space voyage. The spacecraft must therefore be more than a vehicle. It must be a small industrial environment, carrying tools, raw materials, diagnostic systems, and enough flexibility to keep itself alive when individual parts begin to fail. This changes the design philosophy. A short mission can rely on known procedures and limited repair capacity. A Neptune mission must assume that unknown failures will occur long before arrival. Food and water make the duration more concrete. Water can be recycled with high efficiency, but recycling systems require power, filters, chemicals, membranes, pumps, and maintenance. Food is harder. A crew can carry stored food, but over many years the mass becomes large, nutrition can degrade, and variety becomes more important for health and morale. Growing some food on board could help, especially fresh plants that contribute vitamins, texture, and a sense of living renewal. Yet agriculture in space is also a system that can fail. Plants need light, water, nutrients, temperature control, microbial management, pollination strategies for some crops, and protection from disease. A small crop failure on Earth is an inconvenience. In deep space, it can become a nutritional and psychological loss. The farther the mission travels, the more every ordinary requirement of life becomes a maintained machine. Breathing, drinking, eating, sleeping, cleaning, exercising, and working all depend on equipment that must function not for a season, but for a large part of a human career. The mind must live inside the same long duration. There are difficult missions in human history, but most have a visible endpoint within the imagination. A winter in Antarctica ends when the season changes. A voyage across an ocean ends when land appears. A stay on an orbital station ends when the return capsule undocks. Even if the work is dangerous and exhausting, the structure of time remains understandable. A Neptune mission contains a long middle in which departure is far behind and arrival is still years ahead. During that middle, the crew may have no new world to explore, no immediate crisis, and no dramatic milestone. They have maintenance, observation, exercise, experiments, messages, routines, and the ongoing task of staying capable. This can be harder than the moments that sound more dangerous. A crisis focuses attention. A long coast asks people to sustain meaning when little changes. The crew would need personal discipline, shared purpose, conflict management, private space, and a mission culture strong enough to survive repeated fatigue. Time would also separate them from the human world. A crew departing Earth leaves behind family, institutions, politics, science, language, and culture, all of which continue to change. Children grow older, parents age, friends move, marry, become ill, or die. Cities change. Technologies change. The public memory of the mission may rise and fall through cycles of attention. The people on board remain connected by delayed communication, but they cannot participate in Earth's present at its natural speed. By the time they reach Neptune, the planet they remember may no longer match the planet receiving their data. This is not only loneliness, it is temporal displacement. The experience of belonging to a world that is moving through history without them. The crew has not left the solar system, but they have left the ordinary pace of civilization. This is why the travel time to Neptune cannot be treated as a technical inconvenience. It is the condition that gathers all other risks together. Microgravity has more time to work. Radiation has more time to accumulate. Machines have more time to wear down. Relationships have more time to strain. Messages have more time to feel incomplete. The mission has more time to become not an expedition within a life, but the shape of life itself. Reaching Neptune would therefore require more than a faster route or a stronger engine. It would require a spacecraft and crew prepared to turn years of transit into a stable human environment. That may be the hardest demand of all, because the planet is not the only destination. Survival through the journey is its own destination, and it must be reached every day before Neptune can be reached at all. The point of no return on a Neptune mission would not arrive near Neptune. It would arrive much earlier, during the outward commitment from the inner solar system, when the spacecraft has used the energy required to enter its long trajectory and no longer carries enough propellant to cancel that decision. In ordinary travel, turning back feels like a matter of choice. In orbital flight, it is a matter of velocity, timing, and stored energy. A spacecraft is not simply moving through space in a straight line. It is following a path shaped by the gravity of the sun and planets, and changing that path requires changing speed. Every major change demands propellant, and every kilogram of propellant must itself be launched, accelerated, protected, and supported. This is why a crewed Neptune mission would be forced into a severe logic before the planet becomes anything more than a distant target. It would need enough energy to leave Earth, enough to shape the outward journey, enough to correct the route across many years, and enough to slow down near Neptune if the goal is orbit rather than a flyby. Adding enough fuel to return home would not simply double the problem, it would expand it through the rocket equation, the basic relationship that shows how propellant requirements grow sharply as missions demand greater changes in velocity. The more fuel a spacecraft carries, the more mass it must move, and the more fuel it needs to move that fuel. At small scales, this can be managed. At Neptune distance, with a crew, habitat, shielding, supplies, power systems, spare parts, and arrival requirements, the calculation becomes unforgiving. This does not mean a return from Neptune is impossible under every future technology. It means that with propulsion systems close to practical planning, a round trip is far beyond the ordinary structure of human spaceflight. Chemical rockets would make the vehicle extremely large and inefficient for such a task. Nuclear thermal propulsion could improve performance by heating propellant more effectively than chemical reactions, but it would not remove the mass burden. Nuclear electric propulsion could use propellant very efficiently over long periods, but low thrust and power demands would create other constraints. More advanced ideas, such as fusion-based propulsion, are often discussed in relation to very fast outer solar system travel, yet they remain outside the range of demonstrated crewed mission hardware. A mission cannot be built on a hope that a later engine will exist. It must be designed around systems that can be tested, launched, repaired, and trusted. Under that standard, the return leg is the part that begins to disappear from realistic planning. The spacecraft might be able to reach Neptune. It might be able to break into the planet's system with careful design, perhaps using aerocapture in a very distant future or relying on long-duration propulsion. But leaving Neptune again, carrying the crew back across billions of miles, and then slowing safely near Earth would require a second large mission hidden inside the first. That second mission would have to be launched with the original vehicle or assembled and fueled by infrastructure that does not exist. The problem is not only propulsion. A return mission also doubles the demand placed on life support, food, medical systems, psychological endurance, and machine reliability. If the outward journey takes a large part of a lifetime, then the return would add another large part. The crew would not only spend years getting to Neptune, they would need enough health and functioning equipment to repeat the deep space crossing after the work at Neptune is done. The spacecraft that begins the journey would have to remain a viable home, laboratory, and transport system through a duration that may exceed the designed life of nearly every complex system on board. A one-way mission, by contrast, does not become easy. It merely becomes less impossible. It still requires a habitat that can support human life for many years, a plan for arrival, and a way for the crew to continue existing after the main transit. It still raises difficult ethical questions. Sending human beings to a place from which no return is expected would depart from the central tradition of crewed spaceflight. Since the first orbital missions, the basic promise has been that the crew is going away in order to come back. Launch, mission, return, recovery, and reintegration form the structure. Even when danger is high, the architecture points homeward. A Neptune mission with no practical return would break that structure. The crew would not be temporary visitors in the usual sense. They would become permanent inhabitants of a vehicle, a station, or a small constructed environment near a planet where no natural surface can support them. That change would need to be acknowledged clearly before launch. It could not be hidden behind language about exploration or sacrifice. The people selected would need to understand that after the early trajectory is committed, the mission no longer contains a credible path back to Earth. This raises a difficult distinction between risk and design. Many missions carry the risk that the crew may not return. A one-way Neptune mission would make non-return part of the design itself. There is a moral difference between accepting danger and planning an architecture in which homecoming is not included. Supporters might argue that human history contains many journeys from which people did not expect to return to their original homes, and that future settlers could choose such a life knowingly. Critics would answer that Neptune is not a continent, an island, or a frontier settlement with air, water, gravity, and local resources ready to be used. It is a remote planetary system where every moment of human survival depends on machines. Choice matters. But choice does not erase dependency. A crew beyond return would not be free in the ordinary sense. They would be committed to continuous technical maintenance, confined habitat life, delayed communication, and a surrounding environment that cannot forgive prolonged system failure. The point of no return would therefore be more than a mark in the navigation plan. It would be the moment when an ethical idea becomes a physical condition. Before that point, the mission still belongs partly to Earth's ordinary framework of contingency. After it, abort options shrink to small adjustments, safe modes, and survival procedures. The spacecraft may still change course slightly, it may still correct errors, avoid hazards, or alter arrival timing, but it cannot simply come home. In mission planning, this would shape every decision. How much propellant is held in reserve? Which systems are redundant? How much medical autonomy is required? What kinds of repair materials are carried? How much psychological screening is enough? How much authority belongs to the crew when Earth can no longer offer timely guidance? A return-capable mission can sometimes accept certain risks because failure modes include evacuation or rescue. A one-way mission cannot. It must assume that the crew and vehicle are the whole available response. This reality would become part of the crew's daily awareness, not necessarily as constant fear, but as a background fact with operational consequences. A strange vibration in a pump would not be a problem to report and wait over. It would be a local problem that must be understood. A medical symptom would not be evaluated against the possibility of rapid return. It would be evaluated against the supplies and skills already on board. A disagreement about risk would not be softened by the idea that mission control can decide quickly. The crew must make decisions inside the delayed present. The one-way threshold concentrates responsibility because it removes the possibility that Earth can reverse the mission's conditions. Earth can advise, support, analyze, and remember. It cannot retrieve. That knowledge would change the meaning of launch itself. The public might watch the spacecraft depart as an achievement, but for the crew, the deeper transition would occur later, when the trajectory has settled and the propellant margins show that return is no longer part of the possible future. There may be no visible sign of that moment, no dramatic sound, no sudden view, no boundary crossed on a screen that the body can feel. The spacecraft continues outward, the work continues. Meals are prepared, exercise is completed, systems are checked, and messages are sent. Yet in the mission plan, a line has been passed. From then on, Neptune is not only a destination, it is the remaining direction in which survival can proceed. That is the quiet severity of the one-way threshold. It does not depend on Neptune being hostile in appearance. It comes from the mathematics of movement through a large solar system, the mass of fuel, the limits of engines, and the time required to cross empty space. A crew could accept it with courage and clarity, but acceptance would not make it smaller. Reaching Neptune would require leaving behind more than Earth's visible disk. It would require leaving behind the assumption that exploration is complete only when the explorers return. Rescue has always been part of the hidden structure of human exploration. It may be distant, uncertain, or dangerous, but it usually remains imaginable. A ship in trouble can send a distress call. A polar station can wait for aircraft when weather improves. A submarine can be searched for by other vessels. Astronauts in low Earth orbit keep return spacecraft attached because emergency departure is part of the design. Even when rescue is difficult, the idea that help can move toward the people in danger changes the nature of risk. At Neptune distance, that idea loses practical meaning. If a crew is in serious trouble, Earth can know, analyze, advise, and grieve, but it cannot arrive in time. The distance is too large, the travel time too long, and the available response too slow. This does not mean every problem is instantly fatal. It means every problem must be solved locally. The crew and the spacecraft become the entire emergency system. A leak, an illness, an electrical fire. A failed pump, a cracked coolant line, a computer fault, or a damaged antenna is not the beginning of a rescue effort. It is the beginning of a decision made inside the vehicle, with whatever tools, training, and materials are already present. That difference would shape the mission more deeply than any single technical risk. A spacecraft designed for Neptune would need layers of redundancy, but redundancy is not the same as rescue. A backup oxygen compressor can take over when the primary unit fails. A spare valve can replace one that sticks. A second computer can assume control if the first begins producing errors. These measures are essential, but they are finite. The spacecraft launches with a limited store of replacement parts, repair materials, and safe operating margins. Over a voyage lasting many years, those margins are used. A spare installed early in the mission becomes the active part. A repaired system may continue functioning, but with more uncertainty than before. A component taken from a secondary system to save a primary one leaves the secondary system weakened. The vehicle slowly changes from a balanced design into a record of past repairs. Every emergency solved leaves a trace in the remaining capacity to survive the next one, on Earth. Complex systems are supported by supply chains, factories, technicians, fresh materials, and the option to replace entire assemblies. In deep space near Neptune, the supply chain ended at launch. The crew would need a workshop capable of machining parts, printing certain components, testing circuits, sealing cracks, patching insulation, and adapting equipment beyond its original purpose. This capability would be valuable, but it would not remove the constraint. A small machine shop cannot reproduce every industrial process that built the spacecraft. It cannot easily make precision bearings, radiation-hardened electronics, medical drugs, complex membranes, or high-reliability sensors from raw material alone. Some parts can be improvised, some cannot. The crew would live with a detailed inventory of what remains possible, and that inventory would become as important as the navigation plot. The most ordinary failures could become serious because ordinary life in space is continuous mechanical work. Air must circulate, carbon dioxide must be removed, oxygen must be supplied, water must be collected, filtered, cleaned, and returned to use. Temperature must stay within a narrow range. Waste must be managed. Food must be stored or grown. Fire detection must function. Pressure must be maintained. Radiation shelters must remain accessible. Communications equipment must stay aligned and powered. None of these systems can be ignored for long. They do not serve comfort first. They serve survival. A pump that fails in a house is inconvenient. A pump that fails in a closed spacecraft may decide how much water can be recovered before reserves shrink. A fan that fails in a spacecraft may allow pockets of carbon dioxide to collect where the crew sleeps. The environment remains safe only because machines keep correcting it. Medical failure belongs to the same category. A Neptune crew would include extensive medical training, but not a full hospital. There may be diagnostic imaging, surgical kits, medications, sterilization equipment, and remote consultation with doctors on Earth. Yet a serious injury or illness would still be treated inside a moving spacecraft by people whose main professions may be engineering, science, flight operations, or medicine only in limited form. A broken bone, severe infection, kidney stone, appendicitis, allergic reaction, dental abscess, or mental health crisis would be managed without evacuation. On Earth, many of these problems are survivable because the patient can be transported through a network of care. At Neptune, the network is stored in manuals, training, instruments, and delayed messages. The nearest operating room is not physically relevant. The only relevant care is what has been brought along. This would influence even small symptoms. A fever cannot be dismissed casually when no outside clinic exists. A cough, a rash, a persistent headache, a change in vision, or unusual fatigue must be evaluated with care because the cost of missing an early warning is high. Psychological distress would require the same seriousness. Isolation, confinement, grief, conflict, sleep disruption, and years of delayed communication can all erode judgment. A crew member who becomes severely depressed, paranoid, impulsive, or unable to cooperate is not a separate medical issue from mission safety. In a small spacecraft, one person's condition can affect everyone's survival. Countermeasures would be planned, including careful selection, private space, structured routines, exercise, meaningful work, recreation, conflict protocols, and regular support from Earth. But support from Earth would arrive late, and in an acute crisis the other crew members would have to respond first. The spacecraft would be not only home and laboratory, but clinic, repair shop, shelter, and command center. Every role would overlap. Structural damage would be especially unforgiving. Space is not empty enough to be harmless. Tiny particles moving at high speed can puncture or weaken surfaces. Larger impacts are less common. But even small damage can matter when the habitat depends on pressure integrity. Shielding can reduce the risk. Compartments can be isolated. Leak detection systems can locate falling pressure. Repair kits can seal holes or reinforce damaged panels. Still, the basic condition remains. If the pressure shell is compromised, the crew has minutes, hours, or days depending on the severity, and no outside vehicle can dock to help. There is no nearby depot, no rescue capsule, no safe harbour, no planet with a breathable atmosphere. The correct response must happen inside the damaged system itself. The same is true for fire, one of the most dangerous events in a closed habitat. Fire consumes oxygen, produces toxic gases, damages electronics, and can spread through hidden spaces. Fire behavior in reduced gravity or artificial airflow can differ from fire on Earth, making detection and suppression more complex. A Neptune spacecraft would need strict material controls, sensors, extinguishing systems, isolation procedures, and training. But once again, the first and decisive responders are the crew. They cannot wait for emergency services. The emergency services are their own hands, tools, and procedures. This is why the absence of rescue is not a single dramatic fact kept for worst cases. It is a condition that enters routine maintenance. A crew beyond rescue inspects more carefully, because prevention is the strongest form of survival. Every filter change, cable check, software update, pressure reading. An unusual sound matters. The mission becomes a discipline of catching small failures before they grow into conditions too large to control. That discipline can keep a crew alive, but it also creates a constant burden. Nothing is merely broken. Everything broken asks what else will be weakened by fixing it. Nothing is merely delayed. Every delay spends margin. The crew would learn to think in chains of consequence. Because systems in a closed spacecraft are connected, power affects heat. Heat affects electronics. Electronics affect guidance. Guidance affects antenna pointing. Antenna pointing affects communication. Communication affects advice, morale, and science. A problem in one system can move quietly into another, and the crew must see those movements early. Rescue is often imagined as a vehicle arriving from outside. At Neptune, rescue would have to mean something different. It would mean design that prevents many failures, training that prepares for the rest, autonomy that allows decisions without waiting, and repair capacity sufficient for the unexpected. It would mean building a spacecraft that carries as much of Earth's technical protection as possible inside it. Even then, the protection would be incomplete. The universe would not offer a second layer beyond the hull. The crew would know this as a working fact. Their safety would depend on the continued cooperation of machines, procedures, and human judgment, all confined within one small moving environment. That knowledge would make the first sight of Neptune more complicated. The planet would represent arrival, achievement, and scientific promise, but not safety. There would be no harbour waiting there, no station, no repair yard, no medical centre, no stored supplies unless earlier missions had placed them with extraordinary success. Neptune would be a destination, not a refuge. The crew would have crossed billions of miles only to remain inside the same dependence that carried them outward. Failure without rescue is therefore the practical centre of the mission. It is the point where distance becomes more than separation. It becomes responsibility with no external substitute. At Neptune, survival would not depend on the hope that help is coming. It would depend on whether the crew, the vehicle, and the remaining margins are enough. The middle of a Neptune voyage would be the part least visible from outside and perhaps the hardest part to understand from Earth. Launch has a clear shape. Arrival has a clear shape. A spacecraft leaving Earth carries fire, noise, public attention, and the obvious danger of departure. A spacecraft reaching Neptune would produce images, measurements, and the satisfaction of a distant target finally becoming a world. Between those two events lies the long human middle, the years when the mission is not beginning and not arriving, when the crew is simply living inside the consequence of a decision already made. This period would not have the drama of a single emergency, but it would contain a quieter test. It would ask people to remain steady while time itself becomes part of the environment. The spacecraft moves outward every day, yet most days do not feel outward. There is no road passing beneath the hull, no scenery changing through the window, no horizon growing closer. The sun is smaller than it was last month, Neptune is slightly brighter than it was before, and the navigation system confirms progress with numbers and plots, but the body does not naturally feel those changes. The crew wakes in the same compartments, hears the same fans, follows the same maintenance schedules, and moves through the same narrow routes between workstations, exercise equipment, sleep areas, storage lockers, and shared spaces. The mission is crossing the solar system, but daily life is crossing the same few meters again and again. That mismatch between cosmic motion and physical repetition would define the middle years. Routine would be essential. Without routine, the crew would lose structure, and without structure, small stresses could grow. Wake periods, meals, exercise, science work, vehicle inspections, cleaning, medical checks, private communication, recreation, and sleep would all be arranged with care. A stable schedule can protect mental health by giving the day a shape. It can also become difficult because the shape repeats for years. The same meal cycle, the same exercise restraints, the same lighting changes, the same recorded alarms, the same voices, and the same procedures may preserve order, while also reminding the crew how little the immediate environment changes. Variety would need to be designed almost as carefully as oxygen flow. Food texture, personal projects, research tasks, educational material, music, games, private reflection, and small celebrations would not be luxuries. They would be methods for keeping time from becoming flat. In the middle years, even morale becomes something maintained by systems. Social life would be both the crew's strongest resource and one of its greatest risks. A small group travelling to Neptune would have to become more than co-workers. They would be each other's society, emergency responders, medical support, audience, witnesses, and daily companions. In a short mission, irritation can be contained by the knowledge that separation will come soon. In a long voyage, patterns harden, a careless habit, a repeated tone of voice, an unequal workload, or an old disagreement can accumulate force through repetition. The crew would know each other with unusual precision. They would learn fatigue signs, avoidance strategies, preferred silences, small rituals, and private limits. This intimacy could create trust, but it could also remove the normal privacy that helps people reset. Conflict management would need to be practiced, not improvised. The mission would require ways to discuss resentment before it becomes division, ways to rotate authority without confusion, and ways to preserve individual dignity in a place where no one can truly leave the room. Private space would be limited and therefore valuable. A sleeping compartment, a small personal screen, a stored message. Or a few minutes alone near a window could become important beyond its size. Privacy is not only the absence of others, it is the ability to feel that the self has a boundary. In a spacecraft, boundaries are thin, sounds travel, schedules overlap. Personal grief may occur while the next maintenance task is waiting. A crew member may receive delayed news of a death on Earth and still need to attend a systems review, because the vehicle continues to require care. The middle years would contain these quiet collisions between human emotion and mechanical obligation. The spacecraft does not pause because someone is sad. The mission clock does not soften because a family event has been missed. Human life on board must keep moving in parallel with human life on Earth, even when the two no longer share the same timing. The distance from Earth would not only separate the crew from loved ones, it would separate them from ordinary change. On Earth, people are surrounded by weather, seasons, streets, other faces, new rooms, unexpected sounds, and small choices. A Neptune spacecraft would reduce many of these sources of renewal. There may be simulated seasons in lighting, controlled plant growth in small agricultural modules, changing exercise programs, and rotating science priorities, but the larger environment remains fixed. Walls do not become forests, air does not become wind, recycled water does not become rain. The crew would understand the difference clearly. They might value the controlled habitat because it keeps them alive, while also feeling the absence of every uncontrolled feature of a planet. This absence is not necessarily dramatic. It may appear as a longing for unplanned variation, for a smell that was not filtered, for a sound not made by equipment, for a view that was not framed by a window or screen. Science would help sustain meaning, but during the middle year science may also become indirect. The spacecraft can study the interplanetary environment as it travels outward, measuring particles, magnetic fields, dust, solar wind conditions, and changes in radiation. These observations matter. They can improve knowledge of the outer heliosphere and the transition from the more active inner solar system to the quieter regions beyond. Yet for the crew, much of the work would be patient monitoring rather than immediate discovery. Instruments collect data, systems are calibrated, reports are sent, the great target remains ahead. The danger is not boredom alone. It is the sense of being suspended between purpose and fulfillment. The crew knows the mission's largest scientific questions await them near Neptune and Triton, but the years before arrival must still feel worthwhile. Mission design would need to give the middle a purpose of its own, not simply treat it as a long delay. The body would mark time in ways the calendar cannot hide. Fitness records may show gradual changes despite exercise. Medical scans may reveal bone or muscle losses. Radiation badges may accumulate dose. Sleep logs may show periods of disruption. Small injuries may heal more slowly or become more significant because every person is needed. The crew's faces would age in the same enclosed light. Hair would grey. Skin would change. Birthdays would pass with recorded messages from Earth arriving outside the shared moment. The mission archive would show a group leaving Earth as one set of people and approaching Neptune as another. This is not a failure of the mission, It is the natural result of duration, but it would have psychological weight. The destination would be reached by people who have been remade by the act of reaching it. The spacecraft itself would carry the same record. Panels might be patched, labels might fade, tools might bear improvised markings. Spare storage would become emptier in some places and more crowded in others as systems are reorganized. A quiet history of repairs would build into the vehicle. Each solution would show competence, but also consumption of margin. The crew would live among reminders that the mission is aging with them, that shared aging could create attachment to the spacecraft, because it is the only environment that has endured the years with them. It could also create unease, because every sign of wear points toward the same question whether the vehicle can remain reliable until arrival and beyond. In the long middle, hope would need to become practical. It could not depend only on the image of Neptune ahead. It would have to live in ordinary competence, in a pump that still runs smoothly, in a plant tray that produces fresh leaves, in a repaired circuit that holds, in a difficult conversation that ends without damage, in a sleep cycle restored after weeks of trouble. The mission survives not through a single act of courage, but through thousands of controlled repetitions. This is the part of exploration that rarely appears in the clean diagrams and mission animations. The real crossing is not only distance, it is sustained function over time. By the time Neptune grows from a point into a disk, the crew would already have completed a profound part of the expedition. They would have passed through years when nothing outside seemed to arrive quickly, when Earth was too delayed to feel present, and when the destination was too far away to feel near. The middle would not be empty. It would be the place where the mission either becomes a stable human life or slowly loses the conditions that make arrival meaningful. Neptune does not greet arrival with stillness. After years of outward travel, the planet that comes into view is not a frozen blue marker at the edge of the familiar solar system, but an active ice giant with difficult weather. Its visible atmosphere is dominated by hydrogen and helium, with methane contributing to the blue color by absorbing red light. Beneath that outer atmosphere lies a deeper region made of materials often called ices in planetary science. Not because they are cold in the ordinary sense, but because compounds such as water, ammonia, and methane were originally grouped that way when the outer planets formed. Under Neptune's pressure and heat, those materials do not behave like familiar ice. They are compressed into dense, hot states that have no simple comparison with anything on Earth's surface. A crew entering orbit would therefore be approaching a world whose calm colour hides a powerful internal system. The upper clouds may look smooth in distant images, but the measured atmosphere is fast, changeable, and far from quiet. Neptune holds the strongest winds measured on any planet in the solar system. Some winds reach speeds above 1,000 miles per hour, faster than the speed of sound in Earth's lower atmosphere. These winds are not driven by strong sunlight, because sunlight at Neptune is weak. That is one of the central puzzles. On Earth, weather is powered largely by solar heating, by uneven warming of land, ocean, and air. Jupiter and Saturn receive less sunlight than Earth, but they still contain major internal heat and strong atmospheric motion. Neptune is farther out still, receiving only a small amount of solar energy, yet it produces violent circulation. The planet radiates more energy than it receives from the Sun, which means heat is escaping from inside it. That internal heat may help drive its weather, but the exact details remain unsettled. The question is not whether Neptune has energy. It clearly does. The question is how that energy moves through the atmosphere and becomes organized into high-speed winds, shifting clouds, and large storms under such faint sunlight. Voyager 2 gave humanity the only close spacecraft encounter with Neptune in 1989. The flyby was brief, but it transformed the planet from a small telescopic disk into a world with structure and movement. Among the most striking features was a large dark storm in the south, called the Great Dark Spot. It was comparable in size to Earth, though it was not a solid feature and didn't mark a surface. It was a storm system in a deep atmosphere, a rotating region where clouds and gases were moving under conditions not fully understood. Bright companion clouds appeared near it, likely methane ice clouds forming where air rose and cooled. The system showed that Neptune's atmosphere could organize itself on planetary scales, even with little solar energy. Yet the storm did not last in the way Jupiter's Great Red Spot has lasted for centuries. When the Hubble Space Telescope later observed Neptune, the Great Dark Spot seen by Voyager 2 was gone. Other dark storms have appeared and disappeared since then. This changeability matters. It suggests that Neptune's atmosphere is not simply a slower, colder version of Jupiter's. Its large storms may form, migrate, weaken, and vanish on shorter timescales, giving scientists a moving target. A crew near Neptune would not be observing a fixed pattern. They would be observing an active atmosphere where timing matters. A storm present during approach might not survive through the full mission. Another might appear unexpectedly at a latitude where models did not predict it. Clouds can brighten, drift, or fade. Winds can be mapped by watching cloud features move across the disk, but the features themselves are temporary traces, not permanent landmarks. For science, this is an advantage and a difficulty at the same time. Change reveals process, but it also demands patience, repeated measurement, and caution. A human mission would place instruments close enough to follow these changes with far greater detail than distant telescopes can provide. Orbiters, atmospheric probes, and high-resolution cameras could track cloud motion, temperature, chemistry, and magnetic conditions over time. The crew could adjust observations when new features appear, choosing targets more flexibly than a pre-programmed probe. Still, the atmosphere would remain dangerous and unreachable in any direct human sense. No crewed vehicle could descend casually into Neptune's clouds. There is no solid surface to land on. Pressure rises continuously with depth. Temperature increases. Winds shear across layers. Communication through a descending atmosphere would become difficult, and any probe would face increasing mechanical stress until it failed or reached its design limit. The planet can be studied, but not entered as a place humans can occupy. The word arrival therefore needs care. A spacecraft can arrive at Neptune's system. It can orbit, map, measure, and send probes. It cannot turn Neptune itself into a livable environment. The most valuable work would come from instruments placed between human beings and the planet's conditions. That separation would not reduce the science. It would define the science. Neptune's atmosphere also reveals the importance of depth. The visible cloud tops are only the outer expression of processes that extend far below. Methane clouds form where temperature and pressure allow methane to condense. Higher hazes scatter light. Deeper layers may contain clouds of ammonia, hydrogen sulfide, or water, depending on pressure, temperature, and chemistry. Far below, the atmosphere gradually gives way to the dense interior. Scientists sometimes describe Neptune as an ice giant to distinguish it from the gas giants Jupiter and Saturn. The name can be misleading if it suggests a planet made of ordinary ice. Neptune is giant because of its mass and size, and icy because much of its interior is thought to be rich in water, ammonia, and methane compounds rather than mostly hydrogen and helium. These materials are under extreme pressure. Some models suggest that carbon released from methane could form diamond crystals deep inside the planet, which would sink through the interior. This idea is scientifically plausible under certain pressure and temperature conditions, and laboratory experiments have explored related processes, but Neptune's actual interior has not been directly sampled. It remains a model-based inference, not a witnessed event. A careful mission would treat it that way. The possibility is important because it shows how unusual matter becomes inside the ice giants. But it would not be presented as a settled image of glittering storms. It is a question about chemistry under compression, heat transport, and the structure of a planet that formed far from the Sun. Neptune's magnetic field adds another layer to the problem. Unlike Earth's magnetic field, which is roughly aligned with the rotation axis, Neptune's field is strongly tilted and offset from the planet's centre. Uranus has a similarly unusual magnetic field. These strange geometries may be connected to the internal structure of ice giants, perhaps to electrically conducting fluids in shells rather than a deep central metallic core. A spacecraft near Neptune would map that field continuously, watching how it interacts with the solar wind, the thin stream of charged particles from the Sun. Even at Neptune, where the solar wind has weakened and spread out, this interaction matters. It shapes the planet's magnetosphere and affects the environment around its moons and rings. For a human mission, the magnetic field would be both a scientific target and a factor in radiation planning. Neptune is not surrounded by the same intense radiation belts as Jupiter, but charged particles and magnetic conditions would still need to be understood carefully. The planet's rings and small moons add further complexity. Neptune has faint rings, including arcs that once seemed puzzling because material in a ring should spread out over time. Gravitational interactions with small moons help shape some of these structures, though the system remains less familiar than Saturn's bright rings. Near Neptune, the crew would be operating in a region where dust, small bodies, faint rings, and moons are not decorative details. They are part of navigation and hazard assessment. A small particle at orbital speed can damage equipment. A faint ring arc can become important if a spacecraft trajectory crosses it. The mission would need detailed mapping before close operations became routine. Even science around the planet would begin with caution, because Neptune's system is not empty space surrounding a blue sphere. It is a dynamic environment with gravity, dust, radiation, magnetic structure, and moving bodies. The greatest change after arrival may be that Neptune stops being only distant and becomes specific. Its winds have speeds, its storms have lifetimes, its clouds have chemistry, its magnetic field has geometry, its heat has to move from interior to atmosphere through processes that can be tested against data. The planet remains too hostile to touch directly, but it is not beyond understanding. That is the value of going there. A crew near Neptune would not solve every question, yet they could turn many uncertainties into measured constraints. They could watch storms form and fade, track the motion of clouds, release probes into the atmosphere, compare magnetic measurements across orbits, and link what is seen at the top of the atmosphere to what models suggest below. After the long journey, the destination would justify the attention. Neptune is not an inert boundary marker. It is a cold, active, internally powered world, and its weather shows that the outer solar system is not quiet simply because sunlight is weak. The planet's violence is not theatrical. It is physical, measurable, and still not fully explained. Triton changes the meaning of Neptune's system because it does not behave like a moon that formed quietly beside its planet. Its orbit is the first clue. Triton moves around Neptune in a retrograde direction, opposite the planet's rotation, and that motion is difficult to explain if it was born from the same disk of material that surrounded Neptune during formation. Large regular moons usually orbit in the same general direction as their parent planets rotate. because they grow from nearby material sharing the same angular momentum. Triton does not fit that pattern. The most widely accepted explanation is capture. Triton likely formed elsewhere, probably in the Kuiper Belt, the distant region of icy bodies beyond Neptune, and later became bound to Neptune by a gravitational encounter. The details are still studied, but one plausible path involves Triton once being part of a binary pair. As the pair passed close to Neptune, one object may have been thrown away while Triton lost enough energy to remain. That event would not have been gentle. Capture would have placed Triton on a stretched, unstable orbit, and over time Neptune's gravity would have reshaped it. Tides would have flexed the moon, generated internal heat, and slowly circularized the path. In this history, Triton is not merely a companion to Neptune. It is a preserved object from the outer solar system that was taken into orbit and physically changed by that capture. Its surface is therefore valuable in two ways. It may hold clues to the population of icy bodies from which it came, and it may record the consequences of becoming a moon around an ice giant. Voyager 2 gave the only close view of Triton during its flyby in 1989, and the results were unexpected. At a surface temperature near 235 degrees Celsius below zero, Triton is one of the coldest places visited by a spacecraft. Nitrogen, methane, and carbon monoxide can exist there as frozen materials on the surface. Under such conditions, a small moon might be expected to be quiet, old, and heavily cratered. Triton was not. Its surface showed relatively few impact craters compared with many ancient icy worlds, which suggests that geological processes have renewed parts of the crust. There were broad plains, ridges, fractures, and unusual regions with a rough texture often described as cantaloupe terrain because of its pattern of rounded depressions and raised rims. The name is informal, but the feature is real and still not fully explained. It points to internal or surface processes capable of deforming the crust after Triton formed. Even more striking were dark streaks crossing the bright nitrogen ice. Voyager 2 observed active plumes rising from the surface, likely driven by nitrogen gas carrying dark material upward before winds spread it across the ground. These geyser-like features do not require the same kind of heat source as a boiling spring on Earth. On Triton, sunlight is weak but can still warm transparent or partly translucent nitrogen ice, enough to build gas pressure below the surface, depending on local conditions. When that pressure escapes, it can lift particles into the thin atmosphere and deposit them downwind. The result is activity on a world that seems, at first glance, too cold for activity. That distinction is important. Triton does not need to be warm by human standards in order to be geologically and atmospherically alive. Its surface can respond to small amounts of energy because the materials involved are volatile at very low temperatures. Nitrogen, which is a gas in Earth's atmosphere, can freeze and move through seasonal cycles on Triton. A weak atmosphere can form from vaporized surface frost and later collapse or change as temperatures shift. The sun is faint, but over a long season on Triton, even faint sunlight can redistribute frost, change surface brightness, and influence plume activity. Neptune also raises tides on Triton, and the history of capture may have deposited a large amount of heat inside the moon. Much of that early heat would have faded, but its effects could still matter if the interior contains antifreeze compounds such as ammonia or salts that lower the freezing point of water. This is where the possibility of a subsurface ocean enters the discussion. Several icy worlds in the outer solar system may contain liquid water beneath frozen crusts. Europa and Enceladus are the better-known examples because their tidal heating and surface activity are stronger or more accessible to observation. Triton is less certain, but it is scientifically interesting for the same broad reason. It contains water ice. volatile chemicals, a history of tidal heating, and signs of geological renewal if enough heat remains inside. And if the chemistry of the interior lowers the freezing point, a layer of liquid water could persist under the ice. Such an ocean has not been directly detected. It is a possibility built from models, surface geology, density estimates, and comparisons with other icy bodies. A careful mission would not treat it as a confirmed sea. It would treat it as a central question. The question matters because liquid water changes what kind of the world Triton is. Without an ocean, Triton remains a captured icy body with active surface volatiles and a complex past. With an ocean, it becomes part of the wider class of ocean worlds, places where water, rock, chemistry, and energy may interact below a frozen exterior. That would not mean life is present. Life requires more than liquid water. It requires usable chemical energy, suitable ingredients, stability over time, and pathways that can support self-maintaining chemistry. But an ocean on Triton would extend the range of environments where planetary scientists must consider habitability. It would show that even a captured moon near the outer edge of the planetary system may preserve an internal liquid environment long after its formation. For a crewed mission, Triton would likely become the most attractive scientific target in the Neptune system. Neptune itself is immense and difficult to enter, but Triton has a surface, geology, an atmosphere, and active processes that can be studied from orbit and possibly by landers. A human crew would not simply walk across Triton in an ordinary way. The cold is extreme, gravity is weak, the surface materials are unfamiliar, and all movement would depend on suits, vehicles, power, and strict safety procedures. Still, compared with Neptune's atmosphere, Triton offers something closer to a place where instruments can be placed and samples can be collected. Landers could analyze nitrogen ice, methane compounds, dark plume deposits, and surface textures. Orbiters could map gravity and topography to test for an ocean. Radar might probe below the surface if conditions allow. Magnetometer measurements could search for signals that might indicate a conducting liquid layer, though Neptune's unusual magnetic environment would make interpretation challenging. Seismometers, if deployed and able to function in the cold, could listen for internal activity. Plume sampling would be especially valuable, because material lifted from beneath or near the surface may carry chemical clues without drilling deeply. Yet even close study would require restraint in interpretation. A dark streak from a plume is evidence of surface or near-surface activity, not automatically a window into an ocean. A young surface is evidence of renewal, not proof of present liquid water. A gravity anomaly could suggest internal layering, but not by itself reveal habitability. Triton's value lies in how these clues can be combined. Each measurement narrows the range of possible interiors. Each surface map improves the history of resurfacing. Each chemical analysis tests whether the moon is merely cycling frozen volatiles near the surface, or whether deeper processes are contributing. The strength of a Neptune mission would be the ability to build this picture over time instead of relying on one brief flyby. The moon also carries a future instability, because Triton orbits retrograde. Tides raised by Neptune are slowly drawing it inward. Over very long timescales, it may eventually cross a limit where Neptune's gravity tears it apart, possibly forming a large ring, or it may collide with the planet. This outcome lies far beyond any human mission timescale, but it shows that the Neptune system is not permanently settled. Triton was captured, altered, and is still evolving. It is a moon with a past that began elsewhere, and a future that may end by losing its present form. That does not make it less stable for exploration, but it does make it more scientifically unusual. Many moons preserve the history of formation beside their planets. Triton preserves a history of displacement. It began as an outer solar system body, became a captured moon, experienced tidal heating, renewed its surface, maintained volatile cycles, and may still hide internal activity under frozen layers. A crew arriving after the long crossing to Neptune would find in Triton a target more precise than general wonder. It would offer testable questions about capture, heat, ice, atmosphere, geology, and the limits of possible oceans. The moon would not soften the isolation of the mission, but it would give that isolation a scientific purpose. Near Neptune, the most important world to touch may not be the giant planet itself, but the captured moon moving backward around it, quietly keeping a record of how far from the Sun-active worlds can still exist. Neptune is often described as the outermost major planet, but that phrase can make it sound like a border drawn by astronomy, rather than a boundary felt by human beings. The solar system continues beyond it. The Kuiper belt extends outward with icy bodies, dwarf planets, and remnants from the early formation of the planets. Far beyond that, the Sun's gravity reaches into a still larger reservoir of distant objects. By physical definition, Neptune is not the edge of the Sun's domain. It is well inside it, held in orbit by the same star that lights Earth and governed by the same gravity that shapes the motion of the inner planets. Yet for a human crew, the important boundary would not be the formal edge of the solar system. It would be the point where Earth can no longer function as a nearby home. Neptune lies beyond that point. It is close enough in astronomical language to be called local, but far enough in human terms to change nearly every condition that makes exploration familiar. The crew would have crossed a distance large enough to make direct sight of Earth disappear, to turn conversation into delayed exchange, to make rescue impossible, and to reduce the Sun to a weak source of light. None of these changes is symbolic on its own. Each is a physical consequence of location. Together, they create a new human condition. A crew near Neptune would still be part of Earth's civilization. Their spacecraft would be built from Earth materials, designed by Earth engineers, launched by Earth institutions, and guided by knowledge accumulated over centuries. Their language, training, medical care, food systems, scientific priorities, and memories would all come from the planet they left. But civilization would no longer surround them as an immediate environment. It would reach them as signal, archive, instruction, and memory. It would arrive after hours. It would be watched through images rather than through a window. It would support them intellectually and emotionally, but not physically. That distinction is severe. On Earth, even the most isolated person remains inside a living system of air, weather, gravity, sound, other organisms, and possible movement. At Neptune, the crew would live inside a constructed pocket of Earth conditions carried through space. The habitat would be the only breathable atmosphere, the only warm room, the only stable pressure, the only immediate community, and the only place where human life can continue without interruption. Outside it, there is no backup environment. Neptune itself offers no surface to stand on, no air to breathe, no ocean to sail, no land to build upon, and no shelter that human biology can use. Triton offers a surface, but it is a frozen body under extreme cold and low gravity, useful for science only through suits, machines, and careful operations. The crew's relationship with the Neptune system would therefore be one of study, not settlement in any ordinary sense. They could observe, land instruments, collect samples, deploy probes, and map processes that have never been followed closely. They could bring human judgment to events as they unfold, but they would remain dependent on a small artificial world that must not fail. This dependence changes the emotional meaning of achievement. On Earth, discovery is usually shared quickly. A spacecraft image is received, processed, released, discussed, criticised, celebrated, and folded into public knowledge. The discovery becomes part of a common present. At Neptune, a crew might witness a storm changing shape across the blue atmosphere, detect new chemistry in Triton's plume material, or find evidence that strengthens the case for a buried ocean. They would know the importance of the measurement at once. They would send it toward Earth. Then they would wait. The first response would come many hours later, after the excitement, uncertainty, and immediate decisions had already moved on. Human history would still receive the discovery, but not in the same moment as the people who made it. This separation would not erase the achievement. It would make the achievement quieter and more solitary. The crew would become the first witnesses of a part of the solar system that the rest of humanity can experience only after delay. Their work would matter, but the meaning of that work would be carried across time as well as distance. This is one of Neptune's deepest lessons. The solar system is not simply a set of places waiting to be reached. It is a structure that decides how quickly help can arrive, how strongly sunlight can support life, how long machines must endure, how bodies change, and how people remain connected. Distance is not an empty measurement between more important destinations. It is an active condition. It alters medicine, communication, psychology, power, navigation, ethics, and the definition of a successful mission at Neptune. Distance becomes the main environment. The planet's winds, storms, rings, magnetic field, and captured moon are all scientifically important. But the journey also reveals something about the scale on which human life is adapted to function. Human beings evolved in a narrow range of conditions: strong sunlight, open air, gravity, daily cycles, other people nearby, and a world that answers quickly when touched. Spaceflight already challenges those conditions. Neptune stretches the challenge until the original frame almost breaks. The crew would not be beyond the sun's gravity, but they would be beyond the ordinary reach of Earth's presence. That is why Neptune can be called the edge of human belonging without treating it as the edge of the solar system. Belonging is not only a feeling, it is maintained by signals, sight, response, rescue, shared time, and the body's confidence that its environment still makes sense. A mission to Neptune removes or weakens each of these supports. Earth becomes too faint to see naturally. Messages take hours. Help cannot arrive. Sunlight no longer gives a livable day. The spacecraft must replace the planet in miniature. The crew must become more autonomous than any explorers before them. What remains is not abandonment, because Earth would still care, listen, and respond. What remains is separation at the level of physical law. There is no faster reply available by wishing for one. There is no hidden shortcut for a rescue ship. There is no way to make distant sunlight behave like daylight at home. The mission would be limited not by lack of concern, but by the architecture of the universe. This recognition should not make Neptune only frightening. It should make it clearer. The planet is not hostile in a moral sense. It is not trying to keep human beings away. It is a cold, active, distant world following the same natural laws as everything else. The difficulty belongs to the mismatch between those laws and the needs of a fragile biological species. To reach Neptune with a crew would be to carry a small, disciplined version of Earth into a region where Earth itself can no longer assist directly. That act would be extraordinary, but it would also demand honesty. The mission could not be described as simply a longer journey. It would be a change in category, from exploration supported by a reachable home to exploration sustained almost entirely from within. In the final view, Neptune remains both near and far. Near, because it circles the same star and belongs to the same planetary system. Far, because the conditions of reaching it would place the crew outside the human patterns that have shaped every journey so far. It is a world that can be known better, perhaps one day visited by machines in great detail, and perhaps in some distant future approached by people with technologies far beyond the present. But any human arrival would carry a cost written into distance itself. The crew would not only discover Neptune, they would discover what happens to human presence when home becomes delayed, invisible, and unable to intervene. The edge revealed there is not the end of the sun's influence. It is the place where the familiar meaning of home begins to thin, until Earth remains as origin, memory, and signal across the dark. In the end, Neptune remains distant in a way that is difficult to reduce to a single measure. It is not only far in miles, or faint in sunlight, or slow in communication. It is distant because each of those conditions gathers into the others, forming an environment where human life can continue only through planning, restraint, and constant care. The planet itself does not need to become a symbol to matter. Its winds, storms, heat, magnetic field, rings, and captured moon are enough. They make Neptune a real world, active and specific, still holding questions that science has only begun to approach. Yet the greater lesson of reaching it is also about the travellers. A crew there would learn that distance is not empty space between meaningful places. Distance has structure. It delays voices, weakens light, removes rescue, ages machines, and changes the feeling of home. It asks human beings to carry their own environment with them, and to trust that a small enclosed habitat can preserve enough of Earth to keep thought, work, and memory alive. That is why Neptune stands so quietly at the edge of this story. It is not the final boundary of the solar system, and it is not beyond the reach of knowledge. But it marks a region where the old supports become thin, where Earth remains present only through signal and remembrance, and where exploration becomes less like a journey outward, and more like a test of what can still be sustained. The planet continues to circle the sun in its long cold orbit, patient and remote, while the light that reaches it carries only a trace of the warmth that began the voyage.